Welcome everyone to the QU-ATTO tutorial on generation of intense extreme ultraviolet pulses using a seeded free electron laser. Light is more than meets the eye. It is actually the most powerful tool in science. We use light for observation, from peering into the depths of space with telescopes to revealing the tiniest structures inside objects through microscopy. We use light for measurement. Using spectroscopy, we can decode the chemical composition of everything from distant stars to biological samples, all by analyzing the light they emit or absorb. We use light for manipulation. With lasers and other such tools, we're not just observing, we're actively interacting with matter. This enables breakthroughs in physics, chemistry, biology, medicine, and telecommunication. So in every domain, from the very large to the very small, light is essential to discovery. Light is an electromagnetic wave produced by accelerated charges. The diagram shows the broad spectrum of electromagnetic radiation classified by wavelength. In a narrow band of visible light, our eyes perceive the world. At longer wavelengths, in the infrared, we reveal statistical phenomena like thermal emission, but also characteristic vibrational frequencies that are veritable molecular fingerprints. As we move towards shorter wavelengths into the ultraviolet and X-rays, we gain higher resolution, enabling us to explore the ultrasmall, from cellular structures to atoms. The natural timescale of the phenomena we observe also gets shorter and shorter. We therefore also need short light pulses to resolve the time evolution of a system. Light doesn't just illuminate, it reveals, it measures, and it transforms our understanding of nature. We need short pulses of light at short wavelength to resolve the behavior of matter down to its constituent atoms. Atomic fingerprints are shifted to shorter wavelengths between the VUV and the X-rays, as shown in the diagram here. The energy of a photon increases as its wavelength gets shorter. And when the photon energy becomes high enough, it can ionize atoms or molecules. This is interesting and useful, but it also means that matter will absorb the light. And this is particularly relevant in the ultraviolet and X-ray regions, where a single photon carries enough energy to ionize matter. We show here the attenuation length of light in silica, which is an excellent optical material in the visible and near UV spectral range, not so much at the shorter wavelengths we are interested in. To prevent this kind of absorption and preserve the light for experiments or imaging, we have to generate and transport light in vacuum. Accelerated charged particles emit light, and electrons, being lighter, are more easily accelerated than nuclei. We're interested in accelerating electrons in vacuum and make them radiate efficiently. This happens, for example, when we steer a relativistic electron using dipole magnets, which bend their trajectory. That bending causes the electron to emit synchrotron radiation, a powerful broadband light source that covers from infrared to hard X-rays. A more refined magnetic structure is the ondulator. An ondulator is composed of a series of small, alternating magnetic fields that force the electron beam into a wiggling motion, a sequence of tiny bends. What's special is that the radiation emitted at each band interferes constructively. This makes the intensity scale with the square of the number of periods, so more periods mean a much brighter beam. This interference also causes the light to be emitted at specific, well-defined frequencies, giving us sharp spectral peaks. Finally, because the emission is highly directional, ondulator radiation has a very small divergence.
This movie represents the electric field of a relativistic electron following the oscillating trajectory imposed by the undulator field. The leading edge can be seen as an optical wave. Each period of oscillation of the electron generates one cycle of this optical wave. Note how the wave outruns the electrons by one wavelength for every period of the undulator. This is the condition for constructive interference between the light emitted at each band in the undulator. The wavelength for which this constructive interference occurs is given by this equation, where lambda u is the undulator period, a few centimeters, k is the deflection parameter, the strength of the undulator field, and gamma is the Lorentz factor, the ratio between the energy of the relativistic electron and its energy at rest. The wavelength of radiation can be tuned by changing the beam energy, the undulator strength, or the undulator period. In a synchrotron, the orbit of an electron beam passes through several undulators and bending magnets, and the radiation is used by users on many experimental stations. This is an aerial view of the Elettra Synchrotron Trieste site. The circular building is the Elettra storage ring source, where relativistic electrons stored in a stable orbit in vacuum emit light in undulators and bending magnets, serving 28 user beam lines. The second building on the left, with a linear structure tangent to the Elettra storage ring, is the FERMI building, hosting 2 free electron lasers. What is a free electron laser? In order to answer this question, we have to analyze the process of emission from a collection of electrons. The intensity of the light depends on their temporal distribution. As an example, let's take a bunch of randomly distributed electrons, each one emitting radiation with a random phase when passing through the undulator. The total field is given by the superposition of the fields from all the electrons. This superposition can be expressed as the sum of field amplitudes, each multiplied by its corresponding phase factor. We can represent this sum as a diagram in the complex plane, where we add vectors of length proportional to the field amplitude and direction determined by the phase. Adding vectors with random phases is equivalent to adding vectors pointing in random directions. After adding up all the vectors, the total field is given by the distance from the origin. It can be shown that with random phases, the distance is proportional to the square root of the number of emitters. The radiation intensity, which is proportional to the square of the field, is therefore proportional to the number of emitters. This is what happens in a synchrotron, where the synchrotron power is proportional to the beam current. What happens if the electrons are synchronized so to emit radiation all with the same phase, like in this diagram here? When we add the fields from all the electrons, all the vectors will point to the same direction. The total field is proportional to the number of electrons, and the total power will be proportional to the square of the number of electrons. This is a large number. The synchronization can increase the peak power of the emitted light by many orders of magnitude. And this is what happens in a free electron laser. Let's see how the synchronization process works at FERMI. FERMI is a seeded free electron laser. The scheme is called high-gain harmonic generation. At first, the beam is injected in a special undulator called modulator. This plot represents the beam phase space at the entrance of the modulator, the energy on the vertical axis, and the phase, which is the longitudinal position, on the horizontal axis. The green area represents the longitudinal electron density. The beam has a uniform distribution when it is injected in the modulator. The lower plot, at the bottom here, represents the Fourier transform of the electron density. The Fourier coefficients are also called bunching factors. A uniform distribution is non-zero only at the zero Fourier coefficient or the zeroth bunching factor. But the laser beam is injected in the modulator with the electron beam. At the exit of the modulator, the beam is modulated in energy with the same periodicity of the optical wave. This also induces a small density modulation, and you might note that a few bunching factors are different from zero at this position. As a second step, the electrons pass through a magnetic chicane, in green, where more energetic electrons travel a shorter trajectory. So at the exit, they take over the less energetic electrons. Note how, after the chicane, the beam is synchronized in phase, and the Fourier transform of the density contains many harmonics of the fundamental wavelength. This modulated beam is finally injected in a long undulator, where the resonance tuned at one of the higher harmonics of the seed. This selected harmonic is amplified. Let's go back to the Elettra Synchrotron Trieste site and enter the tunnel of the FERMI FEL. Here we are at the beginning of the long linear accelerator of FERMI. We enter the tunnel. The electrons are extracted by a UV laser pulse in the photoinjector. With a total charge of a few hundred picocoulombs, to give an idea, the beam contains approximately 1 part in 100 billion of the electrons present in a single grain of salt. As promised, all happens almost in vacuum. Electrons are accelerated in radiofrequency cavities, which form the accelerator structure. The beam current is increased by magnetic compression. We have a potential of using two compressors to increase the beam current to several hundred of amps. The acceleration continues until a final energy between 900 million and 1500 million electron volts is reached. The final energy is decided depending on the desired final laser wavelength. The beam then passes through the modulator, the dispersive section, and amplifies radiation in a long final undulator for amplification. A magnet separates the electrons from the light, and the electron beam is damped and the light is delivered to one of the FERMI experimental stations. At FERMI, we can do much more. An example is to use the different undulators to play a chord on the FERMI amplifier. Once the density modulated beam is generated, we can select multiple harmonics of the seed, 3 in this example, and configure the amplifier in 3 segments, each dedicated to amplifying one of the selected harmonics. The final pulse will be the superposition of the fields of the 3 harmonics. We may then use phase shifters between the undulators to tune the phase of the 3 harmonics to synthesize a specific waveform, like a train of attosecond pulses, as shown in the diagram. We've turned the complicated story into a very simple one. There is a lot more behind the surface, but this scheme is at the heart of the QU-ATTO doctoral network.
This is where this tutorial ends and where the QU-ATTO project begins.
So thank you for your attention.